really simple load test running on this specific node. I got these guys running as fast as I can. I loosened up the Argon 2 so that they can just pump transactions. So these guys are 5 different accounts and they're pumping a lot of transactions directly to this node. We have some memory collision issues here, as you see the allocate address, just because the random function inside the generating address is kind of showing some weakness, so we need to make that a little bit more, have a little bit more entropy. So a transaction every once in a while will be rejected. But this is multiple transactions per sig chain, so this being 5 transactions and 268 or 300 per, that means about 60 transactions on each sig chain is included in each block. And they all have to be specifically memory sequenced. So this is actually a really, really impractical load test. And what I mean by that is it's showing the most impractical, most arduous tasks to do and seeing kind of how it performs. So this is the node that's actually generating these private blocks. As you see, they're synchronizing between these 2 nodes. They're going into this node, the transactions are being created here, being broadcast to this remote node. This node's in a data center. This node's generating the block, and then broadcasting that block over here for this node to verify it. So you're getting a lot of processing happening here. We see we hit peaks of, let's say, 140 transactions per second right there. And it verified in about 23 milliseconds for something, let's see, 138 and 21 milliseconds. It varies, but this is showing the actual processing time of the block versus transactions per second. So I mean, I obviously don't have enough power on this computer to send. I'm pretty much maxing this computer out, like building the transactions. But if we say like 21 milliseconds, you know, let's do 1,000 milliseconds divided by 21. That's 47 times 130. It's about 6,200 transactions per second that this one specific node could process in this specific type of chain.
It's pretty quick, Cole.
Yeah, I mean, it's not bad. It's not bad. I mean, obviously, we need to get to a mean to start parallelizing a lot of this more. This is really done just in serial right now, and this one's a full quantum. It's using a sig chain and Falcon EC2SA, so, or not EC2SA, sorry, Falcon lattice-based cryptography. So that it has a larger data overhead. Like if we pull, let's say, pull our system monitor. We're going to be monitoring what's happening over on this side. So if we want to look, I mean, you can see my CPU's maxed out. So I'm pretty much at max creation capacity. Here's my CPU. Just, yeah, it's going as much as it can. Network, I'm receiving about 50K per second and I'm sending about 200K per second. So I'm getting pretty close to like pushing this network link. I mean, this network link can do a lot more, obviously, but yeah, you can see, oh, there goes a huge spike of what I'm sending. So the red line is what I'm sending out. Since these guys are broadcasting the transactions to this node, I'm putting a lot of load here. And then since we have this nice asymmetric sequencing, since this computer already has the transactions and it already has them in pre-processing, it only has to run the post-processing and receive post-processed data. So you see this blue line is way lower. And that's going to be kind of the natural case because the transactions are actually received and processed before they are received on a block. So that the block themselves, as you see this block, they're approaching 20 kilobytes right here, but they're processing a pretty large amount. So 140 transactions per second for about 17 kilobyte block. As you know, Bitcoin's like 1 megabyte block and it can do 3. But granted, these are happening a lot quicker in a lot quicker succession. But if you saw the full transaction object being packed with this block, I mean, these probably be, I'd say 100, 200, 300 kilobytes. So it's pushing pretty well. I'm pretty much at my maximum here on this one node. To start to see this scale up more, we need to put the network under more load, which means we need more computers. We need more power to create the transactions because the way Falcon works is it's asymmetric, so it actually takes quite a bit more computational power to one with Argon 2 to generate your keys, and then also to generate your Falcon key. But it's really fast to verify the Falcon key, so that's why we're seeing such small verification times. 20 milliseconds to verify 100, 97 transactions per second. That leaves us a lot. I mean, that's 1/50th of a second. which is nice. So that means that blocks would propagate very, very quickly comparatively to some other implementations.
Nice, bro. You getting pumped?
Yeah, it's fun. It's fun. Yeah, it's good to see. I mean, stress tests bring out new aspects of the code that need to be assessed, and especially this is multi-threading a lot. So we've had a couple race conditions and things like that, but it seems like it's, and you know, we're stress testing the random number generator right here, and we're starting to see, oh wow, OpenSSL's random number generator, it should just generate random addresses is weak. You know, we're only doing about 150 per second, and we're already running into collisions, so we need to add some more entropy there. But other than that, it looks pretty stable. I mean, I've run into a couple little things, but this is kind of our first step towards mainnet hardening, where we see exactly how much it can process. This is simulating a private network, which is slightly different, but Tritium itself will only have about a 650 transaction per second limit based on the block size. As you see, our block size is 20 kilobytes right now. So yeah, it's looking good. It's looking very good. It's a nice real live test situation where it's not just doing isolated post-process or LOP. Most of the benchmark tests have been all isolated. Now this is all of the systems themselves running together, even using the API here. These guys are actually making direct API connections and producing as many transactions as they can per second. And then using the network, this isn't over a local network, so we don't have infinite bandwidth based on our link speed of our router. This is pretty much keeping us as limited as possible in as many different areas, and this has speed of light, latency issues, and then we have computational issues over here as far as like how much I'm limited to be able to produce. But it's looking really nice and pretty consistent and pretty quick, even for a pretty significant load right now. I know Ethereum maxes out at about 17. So this is just one computer. I mean, in this, as you can see, we have lots of runway. If these were running, like one Ethereum block takes about 20 seconds to validate, and they happen every 15 seconds. And that only does 17 transactions per second. This is way far above that. And the beautiful thing is it's decentralized. It's not relying on delegated proof of stake, centralized models. This is pure decentralized processing.